Hello everybody, thanks a lot for coming on this talk. My name is Neil Hickey, and as Michael mentioned, I'm a compiler engineer. I'm not an expert in Vulkan, to be honest, so ask somebody else your Vulkan questions. If you have any questions on SPIR-V specifically, then hopefully I can answer. So my talk today, I want to discuss a little bit where SPIR comes from. So this is the way, obviously, now with Vulkan drivers only consume SPIR-V shaders. So where does SPIR come from? How do you use it in your application? And what are the features that are in there which you can make use of? So SPIR was originally created by the OpenCL working group. So the motivation behind that was they wanted to, obviously when you're developing an application in OpenCL, you ship an awful large part of your application in source, which was a potential security risk, or not security risk, but you could copy your application basically. So SPIR came about as a way of obfuscating that, essentially, so you could ship this IR level. It's a little bit more difficult then to recreate the original shader from the IR. So all the way back in, I think it was 2011, OpenCL 1.1 came along with this optional extension, which was SPIR-V. So moving forward 2 years, OpenCL 2.0 was released, and obviously produced SPIR 1.2. So going forward 2 years, SPIR 2.0 was released. And it had exactly the same objectives. It was tied just to OpenCL. And then when they started working on Vulkan, obviously one of the objectives was Vulkan, as everyone else has been mentioning today, is that it's a very explicit API. There's quite a large overhead in compiling your shaders from GLSL by the driver. So one of the motivations of introducing an intermediate language for Vulkan was to remove some of that overhead. And obviously because we already had SPIR and SPIR working group, it made sense to kind of align on that common format for OpenCL and Vulkan. And as Vulkan was being developed, John Kucinich, who's in charge of the SPIR, or the spec for the SPIR working group, proposed and was adopted, and obviously lots of other people worked on it, a modification of SPIR to SPIR-V. And as I've mentioned, SPIR-V targets both Vulkan and OpenCL shaders. So what is the point of SPIR-V? I've briefly touched on it there, but one of the objectives is to remove the overhead of compiling your shader from GLSL, or indeed from your kernel in OpenCL land, down to the actual assembly that your architecture is going, your platform is going to execute. That's quite a big job in a driver. The compiler is very complicated, it's got a lot of stuff to do. So one benefit, or one main purpose, is it makes it much quicker to recompile those shaders at runtime, because it's in a lowered form. But the other benefit as well is that, as we can see here, an awful lot of these, an awful lot of these languages all of a sudden don't have to be supported by the driver. So it makes your driver an awful lot smaller, one thing. But all of these different shader languages and OpenCL and all these other things don't need to be supported by the driver, which allows us to provide an awful lot of this common compilation. It can be shared across all the companies providing a Vulkan or OpenCL implementation. So that is one of the major benefits, that the Khronos community can come together and develop all of these tools just to target SPIR-V. And then obviously there is a step then to go from that SPIR-V to whatever works well on that architecture. But that's a relatively smaller task. And that's something that each individual hardware vendor can focus their time on. So as I alluded to, there is a developer ecosystem out there. The developer advantage of all that is that there's no difference now between compiling a GLSL shader for one architecture compared to another. They should all behave the same way, which wasn't the case in the past. GLSL written for one application could sometimes not work correctly, or it had different undefined behaviors on a different architecture. So now with SPIR-V, you have that commonality across all vendors. And as I mentioned, it's a lot quicker for your tool to compile down to the actual hardware instructions. So originally SPIR was built, or was very closely tied to LVM, which I don't know if anyone's a compiler engineer here, but LVM is kind of a common compiler framework. So it was very closely tied to a very specific version of LVM, 3.2. What we decided to, and interestingly, it was also an extension in CL 1.2 and 2.0. But what the Khronos group decided to do moving to SPIR-V was to break that dependence. Because we didn't want to have SPIR-V tied to another third-party IP, which we didn't essentially have as much control over. And there was an awful lot in graphics, certainly in JLSL, which is very specific, which wasn't really easily mappable in LVM. So we wanted to make sure that SPIR-V is lossless from that point of view. So everything that you can do in JLSL, you can do in SPIR-V, and it fully supports it. Now this is a core feature in OpenCL, from OpenCL 2.1, and it's also a core feature in Vulkan 1.0. So this isn't an optional thing. And as mentioned, Vulkan, that's the only way you can develop a shader for Vulkan. You have to develop, submit it to the driver in SPIR-V. So how does a compiler look? Well, I mean, as I mentioned, Khronos has developed an awful lot of open source tools which allow you to compile your GLSL or your OpenCL down to SPIR-V. The driver itself will consume the SPIR-V, which has this form. It's a binary format, it's worthwhile pointing out. The intention is not something that you're going to write, it's something you can use another tool to develop for you, but it's the only way that the Vulkan driver can accept shaders. Obviously, most of the tools companies out there, they do use LVM because it's a very useful compiler framework. So we also are developing within Khronos a set of bidirectional translators from LVM to SPIR-V. And that allows the platform developers to more quickly develop their compilers for SPIR-V if they can go to LVM and feed it through the rest of the tool chain. As mentioned, SPIR-V covers both OpenCL, saying SPIR-V, covers both OpenCL and Vulkan. However, these have very different feature sets. One way to enable that within the language is to define these capabilities. So OpenCL will have a different set of capabilities to Vulkan, and you enable them in the binary shader itself. And one of the benefits of this is that from a validation layer, the validation layer will make sure that you only use, or any features you use within your shader, you have to have enabled it explicitly within our capability, or else the validation layer will tell you that it will not work. So these capabilities define a clear set of feature sets that you can then use within your SPIR-V binary. The other thing SPIR-V is a very extensible format, so you can create op extensions. These can create new functionality, new instructions, or change existing semantics to something else. And for instance, the OpenCL built-in functional library is extended into SPIR-V by providing this instruction import, so all the built-in functional libraries appear as an instruction within SPIR-V, but it's enabled by this extension instruction import. So what are the main changes from moving from GLSL shaders to Vulkan shaders? So as other people have mentioned, Vulkan is a much more explicit format. SPIR-V shaders are all in binary, so you can't pass in GLSL to your driver anymore. It won't accept it. It has to accept SPIR-V. Originally, GLSL shaders were all programmed in a high-level language, which is an awful lot easier for a developer to create, of course. But you had to ship your source with your application, which was an issue for some people. And the driver has to compile all those shaders at runtime. The driver has a much simpler job. Now we're just taking the SPIR-V and lowering it from this intermediate language to the instructions that execute on the piece of hardware, which makes the driver's job an awful lot simpler. And as mentioned, because you're shipping an intermediate language, it's an awful lot more difficult for the end user to reverse engineer your output, which is maybe more an issue for OpenCL, but it's still a concern for people working with graphics. So here's an example where you have your GLSL shader on one side, and this is all you need to do now to rewrite this in SPIR-V, which I hope you agree is really simple and straightforward. I mean, I look at that and I can understand exactly what that's doing. So it is more complicated, it's much lower level, but fortunately there are tools that allow you to create what's on the right hand side rather than having to write that by yourself. So there are a number of open source tools that Khronos has developed. One is the GL Spline, which is the reference front end. So that will allow you to produce SPIR-V from a fragment shader, which will be written in something that I will go on to explain in a little bit of time. You can also take that binary format and disassemble it if you really want to look at how the SPIR-V looks, or if you really want to code in SPIR-V directly. I guess you probably could, but I wouldn't recommend it. And similar to an assembler, if you did really want to do that, you could then assemble it into a SPIR-V module again. And something that Hans Christian will discuss shortly after this talk is a tool called SPIR-V-Cross, which allows you to analyze the layouts and the bindings within your binary shader in order to allow you to more easily create your Vulkan pipelines. So obviously the issue with SPIR-V is the driver will not accept anything in a high-level language. So we have those tools that I just mentioned here, but really how do you program your SPIR-V shader anymore? Nobody wants to write it in that horrible format that I put on earlier. That's something for a compiler. Compilers love that, humans not so much. So there is an extension called GLKH or Vulkan GLSL, and that essentially recasts GLSL or recasts SPIR-V in a GLSL-like language, allowing you to directly make use of the extra stuff that's been added to Vulkan in a high-level language. So as mentioned here, it exposes all the SPIR-V features, and it's very similar to GLSL. However, I want to stress here that the intention is this is not something that you ship with your application. This is something that a developer would have to compile offline, and you would ship just the SPIR-V with your application. Because none of the drivers are still going to accept this, this is something that allows you as an application developer to create SPIR-V in the first place. The extension removes some features from Vulkan GLSL. So now you can't just have uniforms at the global scope, they have to be within a buffer object. It's removed atomic counter bindings as well. You can't have subroutines and packed block layouts. Now, I'm sure you all know what they are. Like I said, I'm not a graphics expert, but they're the things that Vulkan GLSL has removed. The things that it's added, which some of the talks are going to go on to at the time, but I'll discuss briefly here. Push constants. These are like very, very fast access uniforms. You push into your shader. Textures and samplers are now separated out. So you create a texture, you create a sampler, and you bind them together at texture lookup time. Descriptor sets, which are a way of grouping objects together in a common set, which then can be updated together in one block, but leaving everything else as constant. Specialization constants, which are quite interesting because they allow you to specify a constant in your shader which you change at pipeline creation time. So I'll go into more detail about what they are and how you use them. And finally, subpass inputs, which allow different fragment shaders to inherit information from a previous shader which is executed. So push constants, as I mentioned, they replace the non-opaque uniforms that I mentioned have been removed from Vulkan GLSL. And they are very, very fast. This is a really fast memory that the driver has access to, the hardware has access to. So you want to put in there something else that you want to be accessed very quickly. And you update them from the driver using this VK command push constants command. And here's an example of using them within your shader. So these are really, really quick and are a really quick replacement for the non-opaque uniforms we have previously. As mentioned, separate textures and samplers now, so you can create a single object, sampler and a texture, which when you want to do the texture lookup, you combine them together using an instruction similar to this. And descriptor sets, as I was mentioning earlier. So when you're specifying your bindings, you can also optionally set the set that it belongs to. So that allows you to, all common objects can be bound together in one common set. If you're going to update them, you only have to update that one set in one go, allowing you to do everything else as constant. This is obviously really useful for, again, speeding up the state changes that you're going to have to make from between shader and location. So the syntax is quite sensible. You just define the set here. You specify your bindings as you would have done previously. And there are commands similarly in the driver that allow you to update those values. Specialization constants. So these can take a constant at shader creation time, which can be overridden by the driver at pipeline creation time. And they can be used for whatever you would use a constant for normally. So arrays of different size. You can use them together in expressions to form new specialization constants, which obviously when you're making your shader at pipeline creation time will be compiled to the correct constant value, but it allows you to reuse the same shader changing constants quite quickly without having to create multiple shading values. And obviously it can be a runtime decision what that value is actually going to be. So they can have a default value. If you don't override them, they'll take the default value. However, you can optionally override them. And additionally, GL workgroup size can be specialized with different values for the X, Y, and Z component, three-dimensional components of the workgroup size. It can be overridden with this special syntax to allow you to specify the local size in X, local size in Z. If I need the local size in Y here will be obviously constant. It won't be overridden by this specialization constant. So the way you set these is from the driver side you create a specialization map. So we have a constant ID which will match the one here. You specify the offset of it, size, and then using that entry section you specify a data, and you essentially map those things together. So you specify your entries here, the size of the data size, and you're mapping it to your data. And then you would push that into the pipeline, and the pipeline will then, when it compiles to a shader, will create the correct format of this constant. Subpass Inputs. So this is a standardized way of doing pixel local storage. So within a shader, you can specify that you want this input attachment. So as you chain multiple subpasses together, which I believe Hans Christian is going to discuss a little bit later, it essentially allows you to pass information from one fragment shader to another fragment shader as you're executing them in your pipeline. Okay, that was quite quick, which is good. So I just want to make sure, so Hans Christian contributed to some of these slides, Benedict Gaster from the University of the West of England, and Neil Henry as well, from the Khronos group. So thank you very much. Are there any questions?
Are there any offline optimizers for SPIR-V at the moment?
There aren't really any at the moment, so I guess optimization, it depends whether it's going to be target independent or target dependent optimization. So anything which is target independent. Sorry?
I was thinking something like what GLSL optimizer does at the moment.
Not that I'm aware of. No, I mean that could come, obviously we could accept that. If it's totally target independent, then it's something that we could provide as well. But no, it's kind of reserved for the driver to optimize the SPIR-V for a particular target.
You mentioned HLSL. Has anybody done an HLSL compiler for the SPIR-V yet?
Not that I'm aware of. There's no reason really why they wouldn't be able to do that. I think it makes sense to do that possibly, but you know, not currently. So if you want to do one, go ahead.
Neil, we're under the impression there are open source projects at least working on it.
Okay.
I don't know if anything's shipping.
Okay, so just to repeat, Tom said there are some open source projects working on a HLSL compiler for SPIR-V, but we're not sure if any are shipping currently. Okay.
Yeah, what level of compatibility is there between OpenCL shaders and Vulkan shaders? Can I take an existing OpenCL shader, compile it into SPIR-V and run it on Vulkan?
No, definitely not. I touched on the capabilities. So there's a separate capability for shader and a separate capability for kernel. So who knows what's going to happen in the future, right? I mean, hopefully OpenCL community can continue to work and there can be a convergence between OpenCL and Vulkan Compute. But currently, there are lots of features in OpenCL which you can't execute on Vulkan. We're ready. Are there any questions on the line?
All lines have been unmuted.
Yes, that's enough. Okay, great. Thanks, everybody.
All lines have been muted.
I'd like to pass over now to Hans Christian, who's going to discuss SPIR-V-Cross, the tool I was mentioning briefly.
Right. I guess you can all hear me?
Right. So I'm Hans Christian. I'm not a driver engineer, I'm a compiler engineer, I'm a demo guy, but I write a lot of Vulkan code, which almost every day, pretty much. I'm going to talk about a new tool that Khronos has released, SPIR-V-Cross. The whole purpose of this tool is to make it much easier to actually use SPIR-V in an application. That's the whole point of the tool. I'm going to first talk about the very first step you have to do. Obviously, you have to get your shaders into SPIR-V with GL slang and those kinds of tools. And then I'm going to cover things like how to create a pipeline layout. Then going on to how to make SPIR-V compatible with other graphics APIs, because as Tom mentioned in the 101, it's very unlikely that you will be able to only support Vulkan for the next few years at least. So ideally we want a way to make SPIR-V compatible with all the APIs. And finally, I'm going to touch into something that's still quite experimental, but could be very interesting, is that it is possible to debug SPIR-V shaders with a C++ debugger, which I'm going to cover last. So getting stuff to run or getting your shaders into SPIR-V is a fairly simple step. Khronos has GL slang tool. There is another tool from Google called Shader-C, which extends GL slang to better integrate with build systems and stuff. It's pretty easy, but it still builds in GL slang, so it's just one code base there. The whole idea is that you should try to compile your GLSL shaders down to SPIR-V in the build system, and that way you get validation in build time, which is much better than loading your game for 10 seconds and saying, oh, it failed compilation on 3 shaders. That's very annoying in GL. But here you can build everything up front and see all the errors. So here I just added some snippets of a makefile that will pretty much do this for you. Another good thing is that there's full freedom for new languages. Like you could write an HLSL if the compiler is there mature, so you could write your own domain-specific shading language, for example. Next thing, after you have built a SPIR-V shader, you still need to create a pipeline, as has been mentioned, and you need that pipeline layout, which you have to pass in when you create the pipeline ahead of time. So what is a pipeline layout? As mentioned, it's pretty much a function signature of your shader. Basically, all the resources you're going to use and where, but you only specify the types. You don't specify the actual content yet, because that's bound in runtime. So just to summarize, what is the pipeline layout here? Well, we have 16 bytes. Well, actually, that's a mistake. That's 64 bytes. 2 descriptor sets. The first descriptor set has a binding there at binding 1, set 1, binding 2, etc. So you might consider, you could write this by hand, right? You could know, oh, my shader does this, I will just write out the layout myself. But consider that if you have a big application, you probably have hundreds, if not thousands of shaders, and you're not going to write that by hand for every single shader. That's very practical. So we need some kind of tool to do this automatically, which is SPIR-V-Cross, what that does. So SPIR-V-Cross is a new tool hosted by Khronos, as mentioned earlier. The whole point is extensive reflection, so that you can do these things in runtime. You can look at SPIR-V and say, oh, that's my layout, and I will give that to Vulkan. Very convenient. And another feature I'll also going to touch on later is decompilation to high-level languages. And this completes sort of a toolbox for SPIR-V, which is going to SPIR-V, messing around with binaries like assemblers, disassemblers, validators. This is more for vendors to implement optimizers, and then to go back again to high-level languages. So the API should be very simple to use. Ideally, we would load our SPIR-V files on disk as a list of integers, feed that to the compiler, get the shader resources, iterate over them, check the descriptor sets and bindings, the name of it, and then create a pipeline layout. It should be very straightforward. We have done that in our internal engine. So those are the simplest things. We want to just check sets and bindings and stuff. But it gets more complicated with push constants, because you have to specify okay, you're using these things, but some of that is used in vertex, some of that is used only in fragments, and in the pipeline layout, you still have to specify what is used in vertex, what is used in fragment. And we can actually do reflection on that, where we check, okay, we have a push constant buffer. For this shader, figure out which members there are actually used by the shader. So if this is a fragment shader, it should only access this one. And we get out here, this is member 1, offset 64, size 16. And we can pass that straight to the pipeline correction. Similarly for input attachment, there's, instead of set and binding, there's also input attachment index. But we can reflect that as well. We can check, okay, our shader has these subpass inputs, and we can query set binding input attachment and give that to the pipeline correction. So now that we can reflect stuff, we can implement this in Vulkan, and it will work fine. But ideally, if you're going to port to more APIs than just Vulkan, then you will have to consider how do I actually use SPIR-V in other languages? How would I use SPIR-V in GL, for example, or maybe DX or something like that? You could say, well, I'm just going to compile to SPIR-V only for Vulkan, but that makes it very hard to take advantage of the new features in Vulkan, because there is no concept of push constants or subpasses or anything in the other APIs. So ideally, we would be able to write our shaders for SPIR-V and make it work everywhere else. And SPIR-V is a really great format. I mean, I'm not a compiler guy, and I could write tools for it just by reading the spec. It's pretty good spec. So we want to make these features compatible, especially with GL first and foremost. And we can. So this is what we have been doing in our internal engine, where we only write for Vulkan GLSL, and we make it work in GLAS and GL, desktop GL as well. So the offline tool chain, we start with Vulkan GLSL. We use shader C or GL slang, it doesn't really matter. We get down to SPIR-V, and we can then validate, optionally, we can validate all our SPIR-V shaders. That's offline, that's done in build time. In runtime, if we have a Vulkan backend, reflect, straight to driver, done. That's the easy part. In, let's say, GLAS, it gets a bit more complicated. We still need reflection. Then we need to look at the Vulkan-specific features and remap them to GL. Then we can decompile it to ESSL and give that to the driver. And that's it. And the good thing about this, we can have a single SPIR-V binary targeting mobile and desktop, no platform if-defs, which would be pretty annoying to test especially. We can use Vulkan features directly instead of having to if-def out that. So probably the most complicated feature is the subpass, where you read from a previous pass. But essentially what this is it reads from a texture of frag port with this thing. So the translation would be translate subpass load to this kind of thing, and make sure that we bind the right textures and so on. That's pretty straightforward. Push constants can be emulated quite easily if we consider that this is really just a uniform struct in old GLSL. That's what we can translate this. We take this thing, make it into a separate struct, make it a uniform, and we're done. Very straightforward translation. And in GL, sure, this is a buffer, but we can use reflection and to stamp out a list of GL uniform calls, which will implement this kind of thing for us. The scripter sets can be a bit annoying because the Vulkan binding model is very, very different from GL, where in GL it's all just a single linear thing per type, whereas in Vulkan it's very different. That just is going to go into it after this talk. But what we can do is look at this, say, okay, this thing has set one, binding one, and we create some remapping scheme to make it work in GL. So after we've parsed it, we can change the declarations and then decompile. Then it works. So we can remap this to, let's say, 4 if we want. That's what the GLSL will look like. There are a few annoying incompatibilities, like instance index versus instance ID. So Vulkan adds the base instance to the instance ID, which is good for many things, but GL does not support this unless someone makes an extension for it. So what we have to do in this case is to add some magic uniform here that the GL backend will have to fill in. But that's what the GLSL will look like. Now it has to add the base instance there. But that will work. It's an ugly workaround, but... So now that we can make it possible to use SPIR-V in GL, there are a few things that are annoying about shaders that are notoriously difficult to debug, especially complex compute shaders, because there is no sensible way to step through a thread on a GPU. It's very, very difficult. GPUs are simply not designed for that. So if you have ever thought, I wish I could assert in a compute shader, things like, I want to add printfs or logging to a shader, you can in OpenCL, but this is not OpenCL. Things like the Clang address sanitizer, which is really useful to figure out undefined behavior with memory access. And things like reproducing a shader bug, running regression tests on an offline farm somewhere. Or things like how to step through a compute shader thread. Then it could be interesting to go to a C++ output and debug it there. So it's still a super experimental feature, but ideally this could be expanded to support basically everything and work really well. The basic idea of this is that if we have a GLM math library, then C++ can be pretty much C++ compatible. And that it would support all the built-in math stuff. It's all the same syntax, except for Swisslang, but that can be worked around. We can reuse the GLSL backend to just slightly tweak it to make it C++ compatible. Very simple. And to deal with resource binding, we can add some macros and scaffolding around the code to make that work. We can expose this final shader as a C-compatible binary interface to make it possible to load it as a DLL or SO or something like that. We could then compile that with debugging symbols and then run that shader and then step through it in GDB or Visual Studio or whatever your favorite debugger is. And I have run a few shader toy array marchers and they take seconds per frame on the CPU. So, but it works if you want that. So essentially what it would look like, you compile down to SPIR-V, output a C++ file, maybe tweak it a little to add some instrumentation if you want, build an SO, and run it. In that test application, you will have to bind specific buffers and textures and stuff. So just to plug, speaking of debugging, there is a new tool that supports Vulkan Debugger, which is the Graphics Debugger. I believe there's a demo of that over in the room over there, which would trace new stuff. This is more of a runtime debugger, though. It supports what you expect. And look at textures and shaders, capture frames, etc. So that was it for me. Is there any question?
I don't know if I'm allowed to ask questions, but how do you handle separate tests and samplers when going back to OpenGL yourself?
Yes, that's the one feature that ignore that it exists.
It doesn't exist. What exists?
What?
What exists?
Oh, so ignore that. So you were talking about separate samplers and textures.
Yeah.
But basically, if you want to be compatible with GL, you can't use those features. There's no way to make it compatible.
So it doesn't look for like static usages and then create combined in GLSL and blah 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 blah. Compiler stuff.
Sorry?
Yeah, like it doesn't look for static usage because if they're not dynamically combined, presumably you could combine them and then create a combined GLSL textures handler.
Right, I assume it's probably possible to work around it, but it would require a lot of work.
Yeah,
Make
okay.
it work in all cases.
Makes sense.
Let's check first question.
All lines have been unmuted.
Right, so lunchtime. So lunch is over in the other room over
All
there.
lines have been muted.
So please help yourself to lunch, and I guess we'll be back at 1:15.
So, actually, in the traditional area is in the lunch place.